Welcome to the first learning outcome, where we get to grips with the Algebra toolkit. Think of it as the language a business uses to turn a real situation into something you can actually solve. Algebra just means using letters to stand for numbers, so we can write a rule down once and reuse it for whatever figure comes along. Across this outcome, we'll dig into quadratic functions and their graphs, expand and factorize expressions, work with polynomials and binomial expansions, and finish with functions and their inverses. Every idea comes with a full worked example, so grab a pen and follow each one through as we go. Before we start solving, let's get 3 words straight. A quadratic is any expression in the form ax squared plus bx plus c, where a isn't 0, and its graph is always that familiar U-shaped curve called a parabola. A root is simply a value of x that makes the expression equal 0, which is where the curve crosses the x-axis. And the discriminant, which is b squared minus 4ac, is a quick number that tells us how many real roots to expect. Let's expand x plus 3 times x minus 5 using FOIL, which stands for first, outer, inner, last. First, x times x gives x squared. The outer and inner pairs give minus 5x and plus 3x, which combine to minus 2x. And the last pair, 3 times minus 5, gives minus 15, so the whole thing tidies up to x squared minus 2x minus 15. And as a quick check, minus 5 and plus 3 multiply to minus 15 and add to minus 2, matching perfectly. Factorizing is just expanding in reverse, and it's how we find the roots. Take x squared plus 7x plus 12. We need 2 numbers that multiply to 12 and add to 7. Running through the factor pairs of 12, 3 and 4 fit the bill, so it factorizes to x plus 3 times x plus 4. Setting each bracket to 0 then gives the roots x equals minus 3 or x equals minus 4. When a quadratic won't factorize neatly, the formula always works, which is handy for something like a break-even calculation. Let's solve 2x squared plus 3x minus 5 equals 0, where a is 2, b is 3, and c is minus 5. The discriminant, b squared minus 4ac, comes to 9 plus 40, which is 49, and the square root of 49 is a tidy 7. So x equals minus 3 plus or minus 7 all over 4, which gives x equals 1 or x equals minus 2.5. Completing the square is a neat way to rewrite a quadratic and read off its lowest point, which in business might be the output that minimizes your cost. Let's put x squared minus 4x plus 1 into the form x plus p, all squared plus q. Half of minus 4 is minus 2, so we start with x minus 2, all squared, but that expands to x squared minus 4x plus 4, which is 3 too big, so we subtract 3. That gives x minus 2, all squared, minus 3, and it instantly tells us the minimum point sits at 2, minus 3, with the line of symmetry at x equals 2. The discriminant b squared minus 4ac quietly decides how many times a curve meets the x-axis. If it's greater than 0, you get 2 distinct real roots and the curve cuts the axis twice. If it's exactly 0, there's a single repeated root where the curve just touches the axis. And if it's less than 0, there are no real roots at all. Take x squared plus 2x plus 5. The discriminant is 4 minus 20, which is minus 16, so this one never meets the x-axis. Here's a classic where a straight line meets a curve, rather like a supply line crossing a demand curve to settle on a price. We're solving y equals x plus 1 together with y equals x squared minus 3x plus 4. Setting the 2 right-hand sides equal gives x plus 1 equals x squared minus 3x plus 4, which rearranges to 0 equals x squared minus 4x plus 3. That factorizes to x minus 1 times x minus 3, so x is 1 or 3, and substituting back gives the 2 crossing points, 1, 2, and 3, 4. A polynomial is just a sum of terms with whole number powers, running from something like an x cubed term all the way down to a constant. We can add, subtract, and multiply them by collecting like terms, and two handy shortcuts save a lot of long division. The remainder theorem says that dividing f of x by x minus a leaves a remainder of f of a, and the factor theorem says that if f of a equals 0, then x minus a is a factor. Let's find the remainder when f of x equals x cubed minus 2x squared plus 3x minus 4 is divided by x minus 2. Rather than doing any long division, the remainder theorem tells us simply to work out f of 2. That's 8 minus 8 plus 6 minus 4, which comes to 2. Since the remainder isn't 0, x minus 2 is not a factor. Now let's show that x minus 1 is a factor of f of x equals x cubed plus 2x squared minus 5x plus 2. We test x equals 1, 1 plus 2 minus 5 plus 2 equals 0, so x minus 1 is indeed a factor. Dividing through leaves x minus 1 times x squared plus 3x minus 2. That remaining quadratic has discriminant 17, which isn't a perfect square, so its roots are x equals minus 3 plus or minus the square root of 17, all over 2. Splitting a complicated fraction into simpler pieces, called partial fractions, makes it far easier to work with. Let's express 5x plus 1 over x plus 1 times x minus 2 as a over x plus 1 plus b over x minus 2. Multiplying through gives 5x plus 1 equals a times x minus 2 plus b times x plus 1. Letting x equal 2 gives 11 equals 3b, so b is 11 over 3. And letting x equal minus 1 gives minus 4 equals minus 3a, so a is 4 over 3. Counting problems bring in some new notation. A factorial, written with an exclamation mark, means you multiply a whole number down to 1, so 5 factorial is 120, and by convention 0 factorial is 1. NSER is the number of ways to choose r items from n, worked out as n factorial over r factorial times n minus r factorial. And a binomial is simply an expression with two terms, like a plus b, whose powers we're about to expand. Let's expand 2 plus x, all to the power 4, using the row of Pascal's triangle, 1, 4, 6, 4, 1. Those coefficients multiply falling powers of 2 and rising powers of x, so we get 1 times 2 to the 4th, then 4 times 2 cubed x, then 6 times 2 squared x squared, and so on. Working the numbers through gives 16 plus 32x plus 24x squared plus 8x cubed plus x to the 4th. Notice the powers of 2 fall from 4 down to 0, while the powers of x climb the other way. The binomial expansion also works for powers that aren't positive whole numbers, which is handy for quick approximations. Let's expand 1 plus x to the power minus 1, up to the term in x squared, which is valid when the size of x is less than 1. Using the formula, the first term is 1. The term in x is minus 1 times x, so minus x. And the term in x squared is minus 1 times minus 2 over 2 factorial, giving plus x squared. So 1 plus x to the minus 1 is approximately 1 minus x plus x squared, carrying on as an infinite series. The difference between permutations and combinations comes down to whether order matters. Permutations count arrangements where order counts, using NPR, for example, awarding gold, silver and bronze to 3 of 8 runners gives 8p3, which is 336. Combinations count selections where order doesn't matter, using NCR. Picking a team of 3 from 8 people gives 8c3, which is 56. The same 3 people can win the medals in many orders, but they only make one team. A function is just a rule that turns each input into exactly one output, like f of x equals 2x plus 1. The domain is the set of inputs you're allowed to feed in, and the range is the set of outputs that come back out. In business terms, you might think of the domain as the quantities you could order and the range as the prices you'd end up paying. A composite function means applying one rule after another. Given f of x equals 2x plus 1 and g of x equals x squared, let's find fg of 3, remembering that fg means do g first, then f, so g of 3 is 9, and then f of 9 is 2 times 9 plus 1, which is 19. In general, fg of x is 2x squared plus 1, and order really matters because the other way round, gf of x gives 2x plus 1 all squared, which is completely different. An inverse function simply undoes what the original did. For f of x equals 2x plus 1, we write y equals 2x plus 1, then swap x and y to get x equals 2y plus 1. Rearranging for y gives y equals x minus 1 over 2, so the inverse is x minus 1 over 2. On a graph, a function and its inverse are mirror images in the line y equals x. The exponential function e to the x and the natural logarithm, ln x, are a perfect inverse pair, each one undoing the other. That means ln of e to the x is just x, and e to the ln x is also x. Because e to the x is always positive, ln x is only defined for x greater than 0. As an example, to solve e to the x equals 20, we take len of both sides, giving x equals ln 20, which is about 3.00. Let's gather the threads together. A quadratic, ax squared plus bx plus c, can be solved by factorizing by the formula or by completing the square, which also hands you the vertex. The discriminant tells you how many real roots there are. The remainder and factor theorems tame polynomials, and partial fractions break awkward fractions into manageable pieces. Add the binomial expansion, the counting rules, and functions with their inverses, and you've got a genuinely powerful algebra toolkit. That brings the first outcome to a close, having taken us from quadratics all the way through polynomials, binomial expansion, and inverse functions. The real skill now is practice, so do work each example through by hand until the methods feel automatic. To build on this, the reading list points you towards Core Maths for Advanced Level and the CGP revision guides, while sites like Maths Genie, Dr. Frost Maths and Khan Academy offer plenty of worked solutions and video lessons. And remember, the unit's ebooks on Moodle are there whenever you'd like a steadier walkthrough.